Karim Ruval-Kaba, who is going to talk us through a project that we've all got a vested interest in, which is food. And that's about critically how to minimize loss and improve yield. So handing over to you, welcome to everybody that's watching. Over to you, Karim. Talk us through what your project is.
Hello, can you hear me?
Yes, we can
Hello?
hear you, Karim. Yep.
Okay. Sorry. I have a little bit of delay. So I'm sharing my screen. So thank you everyone for having me today. As Mike already shared briefly, I'm gonna talk to you a small presentation about what was mainly the talk of my PhD, the main project, which was a cooperation between Friedrich Schiller University Jena, AMS Osram, and Fraunhofer IOF Institute of Photonics. So let's get started with the motivation, what it was really interesting into my project. Um, so let's talk about the main relevance, the main motivation for me to doing this project. So we have currently 1/3 to 1/4 of the food that has been produced globally ended up either being lost or waste. This represents 1.05 billion of tons in terms of volume, and this represents $1 trillion US in terms of monetary losses annually. So there are many factors that contribute to these global food loss, but primarily we can detect these with the ideal harvesting time. And this happening is a really huge problem because when we harvest, it happens once in a year, and it's for every fruit that we have on the crop. That means that whether the fruit is already ripe or not, whether it is overripe or underripe, it's going to be harvested at the same time. So we need to mitigate this problematic. So in order to mitigate this, I came to the solution doing a photodiode array using two detectors in order to determine the fruit maturity. I see two main applications in different industries. The first application into the industry is with the so-called precision agriculture. We can see here farming drones and farming robots that are scanning every single fruit and is determining whether these fruits are already ripe or not. This is a pretty futuristic image, but the immediate application will be into the smart sprayers, where we can see here on a sprayer we will have a ton of these photodiodes, a lot of these sensors that are going to start scanning the plants that we have on the field, and it's going to determine what is the required amount of water that every single of these plants will need. Another application will be to the one machine, a harvester that is scanning the fruits that are in the tree, and it's going to be calling the ones already ripe. So another application that is going to go immediately to the consumer side is going to be a supermarket scanner, where we can actually just take the fruit, go directly into the supermarket, and we'll know what is the ripeness degree of this fruit. But if we have already these kind of applications right now, it's not crazy to think that we can have an implementation into our cell phone, into a mobile fruit scanner. So this is the motivation and the relevance of this project. Now let's go into the data, what I have done previously. Since the year 2023, where I take an 18-week long experiment. And here already you can see on the left side, what is the transition from an apple that going through the flower onto what we know as an apple reddish. When we can see already here with only an RGB photo, the transition on the pigments between the week 12 and the week 13, flowing from greenish to yellowish. And little by little, we can see how this pigmentation is actually turning into red. This is what we can see with just with a photo. Now let's see what we can see with the spectrum. In terms with the spectrum, we see here a really broad band that goes from the visible, starting with the 400 nanometers, and up to the wire, right into the 2300 nanometers. And for here, you have 12 spectral bands that are really relevant, starting with the carotenoids at 480 and thionsinates at 550, two spectral bands for the chlorophyll at 770 and 700, and normalization band that is really important in this project because it was the normalization band, because here you will have the structurally intact internal plant tissue. It's related to actually how healthy is the plant. In order to do this, you have an homogeneous scattering. And here you can also, in terms of the NIR and wire, 5 spectral bands in the OH overtones and 3 spectral bands for the CH overtones. Here it looks a little bit messy, but now that it's been defined and thanks to this normalization, you can see how the chlorophyll it started getting to be decremental onto the week 12. When here we have seen here transition from the pigments, and now the relevant is going to be more into the 480 and 550 up to the week 18, which is the end of experiment where the fruit's already ripe. When we go to the NIR and S-wire, we see that the farther that we go into this wire, we see that it's more sensitive, the measurements. So we see here a spot on the week 12. When we look into this window between the 1450 and the 7070, we see a major spot that goes here onto the week 12. And suddenly we found here the spot where everything is stabilized, kind of a thing. But it's going into this region from the S wire. But if we go into the edge, onto the close to the edge onto these measurements, we see that here actually you see an arm that is going downwards. But all of a sudden you see a transition. Instead of going downwards, you have an upwards transition. So it was a phenomenon that we have, especially in this one on the 2180 nanometers. And this is in terms of spectrum. You can actually group this in only 5 molecular groups. You can see here the transition on the carotenoids, that is, you have an exponential growth since the week 2 until the week 18. Then you see the same transition from anthocyanins starting from the week 6 until the week 18. And the chlorophylls, that's in the week 1, you have a exponential decay. And if you look then afterwards to the CH and OH overtones, here I just pointed out one band from the close to the NIR. So you can see that the farther you go, the more contrast you will have in your measurement. But now you see here this spot that I just mentioned, that you have a maximum on the week 12. This is can be translated to the fruit development diagram, where you have the stark accumulation, and then you see here a transition actually on the week 12, when you have no more stark accumulation but a stark decline. And this we can actually perceive it. We can perceive this now thanks to the disnormalization technique and thanks to the S-wire and the spectral bands that we here seeing. This is in terms of a spectrometer measurements, but if we talk about a sensor, obviously we would like to have this really small package and small design. So for this, I have used 2 detectors, one based on silicon and the second one based on a 3-5 compound material. And this is primarily the configuration that you will need for your sensor, where if you want to do a production assessment, you will need to focus on these spectral bands that are going more close into the S-wire. But if you want to do an application in the post-harvesting assessment, then you will need to look into the NIR bands. And so the most relevant key feature about this application, about this project, is the small size and the low cost that will provide it as well. Since you can see already here, the sensor itself, it's smaller than 2 euro cent coin. And if you integrate with the light sources, well, it's going to be a little bit bigger than the 2 euro cent. But in terms of, if you compare it in terms of size and in terms of cost to an spectrometer solution or a hyperspectral band, a hyperspectral camera, it's the prices are gonna be way lower than a typical application that you will find on the market. So that's pretty much everything for my presentation. And Ray, I'm open to your questions.
Thank you. That was interesting. I mean, the obvious question is, have you shared this with the people doing the work on the ground? Have you been able to take this into a kind of a food manufacturing environment or an agricultural environment to get some sort of feedback on the proposition?
Until now, we work closely to the farmers. We have the direct supplier where these people provide us different types of cultivars of apples. So we test this experiment and was designed based on different cultivars of apples and also with avocados. If you also are interested, this is another slide that I have just prepared that you can also have the same behavior, the same test on avocados on the field. This is primarily the two fruits that we have tested. But directly from the field. But I have also made tests from supermarket tomatoes and pineapples, for instance.
I was going to say, I was wondering why apples actually, and then avocados is quite logical. I'm sure we've all had rotten avocados that seem fine,
Yeah.
when you pick them up in the supermarket and things. So no, it's really innovative. And when you were developing the project idea, presumably that cost dynamic of the, that very low cost unit costs that you've kind of identified was pretty critical to the scaling. Did that
Yeah.
kind of, was that a kind of absolutely central proposition right at the beginning, or did you work that out as you were kind of understanding the technology potential?
No, since the beginning, it was the main target. Since with AMS, the main target is photodiode sensor, really simple solution to bring it into the market. So
Yeah.
since the beginning was the idea to bring a low cost solution that we know that, okay, with a hyperspectral camera, with a spectrometer, you will have the major resolution. but you want to make this for a consumer, and you want to expand the manufacturing costs.
Yes, yeah. It seems to me as a sort of non-scientist in the room, if you like, this kind of constant push and pull between customization and kind of scalability seems to be the absolutely kind of critical back and forth that you see around all kind of product and project development, from my side. Thank you. I'm really conscious of time. We've got quite a lot of great presentations to go through. By all means, anybody watching, drop a note in the chat, but also critically, contact details are on all these decks. So get in touch with these great presenters because these projects are truly innovative and worth your attention and follow up. Okay, next we're going to come to the topic or the category area, I should say, of photonics and optical sensors. We have a short list of 3